Okay, maybe we'll go ahead and get started now. Welcome everyone to the Air Sea Fluxus from Space webinar. Today, by at least Megan's accounting, this is the 100th webinar. So it marks a certain longevity in this series in really trying to articulate the opportunities and the capabilities in measuring the air-sea interface from satellites. So, and we're really happy today to have Seth Zippel presenting, not only because he has great results to present, but also because he gave the very first webinar almost 4 years ago. Um, so to celebrate the 100th webinar, we should be offering champagne um, and snacks and everything, but you'll have to take those virtually. But I'll let Seth take it away. He's going to talk about energy and stability theory in the wave-affected surface layer of the atmosphere.
Thank you, and thanks for inviting me back. I'm going to share my PowerPoint here. Um, if I remember correctly, the talk I gave last time was on similar topic, but on the ocean instead of the atmosphere. So today I'll be switching sides of the interface and talking about energy and stability um, above the water, but close enough to the surface where the waves still have influence. Um, so for those of you who don't know me, I'm Seth Zippel. I'm an assistant professor at Oregon State University. And to talk about this, I will be focusing on measurements made from this tower. Can I get a thumbs up or something if you're seeing the right screen really quick? Great, thank you. Um, This was an NSF-funded project, started when I was still at Woods Hole before I moved to Oregon State. So it is from Buzzards Bay in Massachusetts, which is right next to Woods Hole. Um, and really a lot of thanks and help went to my co-PIs, Malcolm Scully and Jim Edson, who taught me a ton throughout this project. So one of the questions and one of the motivating goals here for me was relating some of these really small scale fluid mechanics of fluid flow over surface waves and how they relate to sort of the more general bulk idea of air-sea exchange of heat, momentum, and gas that we talk about when we talk about things like bulk flux algorithms and boundary layer theory. What that looks like, the small scale fluid flow. This is an image from paper by Sullivan et al. In 2018 from large eddy simulations showing how difficult this flow field can be, how complex it can be um, when you have wind blowing over waves. Um, and somehow we get from this picture into something like this. This is a snapshot from Jim Edson's 2013 paper about core 3.5, showing that, we have this sort of bulk relationship between the wind speed, the 10-meter neutral wind speed, and the wind stress, which is applied really commonly for estimating bulk fluxes from measurements of mean speed and air temperature at sea, and also in lots of models and um, that need a boundary layer flux. Okay, so I'm going to do a pretty try and do a pretty extensive background here and make sure everyone's on the same page. It involves two sets of literature that aren't always considered at the same time. So I'll do some on turbulence and boundary layers and some on surface waves and wind wave growth, and then I'll get into connecting them with these measurements. Um, all right, so if we have a non-wavy boundary, if we have a neutral boundary layer flow over flat plate, it's still a fairly complex flow. This is an image of laser fluorescing dye. Um, the video is actually really beautiful. I love just the complexity you see in these turbulent flow fields. But this is sort of the base case that we're trying to describe. And it's really hard. There's a lot of complexity in all of these eddies. And so we tend to describe the mean profile of velocity throughout this boundary layer. The boundary layer height is roughly here, the extent of these turbulent eddies. And some of the early theories focused on what's called the overlap layer of the boundary layer. So this is defined by heights that are far enough away from the wall that the viscous effects aren't very important, but also far enough away from the outer edge of the flow, delta, so that the length scale delta isn't relevant to the flow. So in this region, because you're far from viscous effects, you're far from delta, if you want to scale the velocity shear, you only have uh, two parameters. You have U star, which the friction velocity, essentially the stress or the force the flow is pushing on the boundary expressed as a velocity, and Z, the distance away from that edge, right? We can't use viscosity, and we can't use delta as scales. So this is really the only way to scale. Kappa here is a constant of proportionality for the length scale. And if you integrate this, you can get a velocity profile. The integral of 1 over z gives you a log function. And there's a constant of integration, which for now we'll just wrap into this z naught parameter in the log function here. So this is what's called a flux profile relation because it relates the flux or U star, the stress on the boundary, with the profile of velocity, U of z. It's a very useful relationship. It allows us to translate a measurement of U into an estimate of the stress or the force on the boundary, U star. It depends on one parameter right now, roughness, and there's one constant, kappa. Now, there's a turbulence balance that goes with this velocity profile from the scaling also. In the TKE budget, we would have a balance of the production of energy, of turbulent kinetic energy, due to the Reynolds stress working on the shear profile and the dissipation rate, both of which would scale as U star cubed over kappa z, which will come up a little later. All right, so this is in a neutral profile with no waves. What about if we have a non-neutral profile or if we have buoyancy or density effects in the boundary layer? Um, this was tackled by a paper by Monin and Obukov in the 50s, 1954, who used additional scaling arguments to suggest deviations from that log profile and the velocity. So essentially for unstable conditions, there's additional mixing due to the buoyancy flux at the interface, and that tends to reduce shear from what you would expect from this log profile. Similarly, if there's stabilizing conditions, some of that turbulent energy goes into mixing density rather than shear, so you tend to have more shear than you would expect from the neutral layer. So the modification to the scaling is done with this function phi sub m for shear and phi sub epsilon for dissipation rate. Um, and these phi functions are assumed from these scaling arguments to depend on one parameter only called the stability parameter, sometimes expressed as zeta. Sometimes you see it as z over L. Capital L is called the Monin-Obukov length. Similarly, in our TKE budget, if it's scaled, we no longer just have production equals dissipation. We have a buoyancy flux term. And when we scale it, then we get a similar relation for these phi parameters and zeta, which sort of bound them together. So they're puts some constraints on what we can have for phi sub m, phi sub epsilon. But for the most part, there's no analytic solution for these scalings. We can't integrate like we did easily for the 1 over z layer. So they have to be determined empirically, but we can be guided with some of these physical equations on how they relate to each other. All right, and so this is typically what we call Monin-Obukov similarity theory or MOST or MO theory. There's lots of different names for it, but it describes these flux profile relationships in a boundary layer, which are incredibly useful for determining things like momentum flux and heat fluxes. So it took a few decades after this paper in the 54, the 1960s and 70s, there were the so-called Kansas and Minnesota experiments to determine these empirical functions. Why Kansas and Minnesota? Well, they were looking for very horizontally homogeneous terrain. My partner's from Minnesota, and I love ribbing her about this one. This is an image of the flux tower that they used in the Kansas experiments. Um, so essentially, they had several levels of mean wind speed, turbulence, heat fluxes, and were able to determine a functional form for that phi m parameter. So here's image taken from one of the papers in the I believe this one was from Businger, showing, they actually get this really clean, tight relationship with for their phi m scaling with zeta, that stability parameter. All right, so this is over land. A lot of the focus here is over the ocean for this group. So it took a while later, much more difficult to logistically to get similar flux measurements over the ocean. It takes expensive platforms or towers or unique platforms like Flip. Um, but we end up seeing fairly similar results with wind and turbulence profiles over the ocean. So this seems to work pretty well if you change the stability function a little bit from the overland functions, Businger Dyer functions. But this has resulted in um, confirmation and better understanding of wind profiles over the ocean. All right, so as a few comments, so far, this is seen to give pretty good average turbulent fluxes. We've been using these bulk flux algorithms for a long time. They work fairly well. They're a really good, first order estimate of fluxes over the ocean. But we haven't included surface waves at all, right? We have sort of left this Z-naught roughness parameter to be determined. That's really important for the specific form of these coefficients, the exchange coefficients, the ocean. And so one way to incorporate the effects of surface waves would be through the roughness length, this roughness parameter. Um, Essentially saying the waves only interact with the boundary layer in setting the roughness at the interface. And it's been shown by lots of various people, not just by this Core 3.5 paper, that there's correlations between the drag coefficient and various wave parameters like wave age and wave steepness and other combinations. So you can use bulk wave parameters to help set the roughness, Z naught, and therefore the drag coefficient. But because there's a really tight correlation between wind speed and the wave state, you can also use wind speed fairly successfully in these bulk algorithms. All right, to dig a little deeper into understanding more of the specifics of those small scale fluid flow features that are important for setting this roughness over waves, we have to dig a little deeper into the wind wave literature. Now, this turbulence literature that I've very quickly overviewed goes back about 100 years. A lot of the folks working on boundary layers were doing so in the early 1900s. The wind wave literature goes back almost even farther than that. For a long time, people have been wondering why waves exist on the water surface. And so the literature for understanding how waves grow from wind goes back to the 1800s. So I am going to do a very quick overview. It cannot be comprehensive just because of the volume of literature on this. And I naturally will then have to select some highlights, which can always be tricky. So just know that there's more out here than I'm presenting, but I'm giving a very quick overview. And the current understanding from still water, if you have initially unperturbed flat water, there's a thought that from so-called Phillips theory, which was developed in the mid-1950s, that there's existing pressure patterns in the turbulence and the airflow over the waves. This broad, 2D in space or 3D in space really, but 2D on the surface and then advecting and moving in time creates some pressure that is advecting over the surface that is resonating with a nascent mode of a water wave at very small scales. And so this type of resonance can create wave growth from nothing, but it turns out it's a linear growth rate, which is too small to explain the, the mean growth with fetch and time that we tend to observe in the ocean. So this can explain the growth of waves from flat water, but it doesn't give us the whole picture because it can't grow waves quite fast enough to explain what we see um, in out in the real environment. About the same time, there was another theory that was proposed by Miles, now referred to as Miles theory, that does give exponential growth. It's essentially an instability solution, but this requires that the wavy perturbations already exist, so it can't explain the growth of these waves from flat water. But if you have waves, you can grow them exponentially with this type of solution. I'll go over this a little bit more later. Um, these papers were published in the same year from Miles and from Phillips. There is a much earlier theory from Jeffries from the 1920s that has been uh, coming back a little bit. The idea that instead of that, the steepness of waves can cause flow separation um, across the wave crests, and this creates pressure pattern of high and low pressure, the lee and windward side, that has a phase such that it grows waves. So the early measurements after Jeffries put this theory out in the 20s suggested that it wasn't couldn't quite explain the growth rates that we observed, but it's coming back that this might be of interest at much higher wind speeds and still exist. Okay. So these are three big ones that get cited a lot. There's many more that I don't have time to mention that have discussed this, including ones like Belcher and Hunt that are a lot more recent. This is just to give a surface level overview. Um, and so the good thing about these is they let us, a lot of this theory has been coded into spectral wave models. So for simulating waves regionally, globally, um, we tend to evolve the wave elevation spectrum, which includes source terms from the wind. These include those linear growth terms, exponential growth terms, and this wind wave input can be linked to roughness length. There's several papers about this parameterization, this relationship between the wave supported stress, which is related to this wind wave input, the energy input by a phase speed, and that relation to the total stress that have been presented by Janssen in several papers, most recently this one in 2023 about very high winds. Okay, so this gives us a way to connect a wave spectral model with that roughness length, which connects it to the fluxes in the boundary layer, moving a little bit beyond just the bulk of parameters that you would put into something like core. All right, so a little bit more about this exponential growth. I'm going to dig a bit more into Miles' theory. So Miles essentially did an instability analysis. You might be familiar with this in other aspects of oceanography or fluid dynamics, things like often considered an instability analysis, the Orr-Sommerfeld equation with nu, the Rayleigh equation, the Taylor-Goldstein equation is seen a lot of in oceanography, especially as it pertains to things like KH instability. Essentially, Miles solved the Rayleigh equation. So without density or without viscosity. Um, and this with a mean logarithmic profile for a neutral boundary layer, and then a density jump at the interface between air and water, you get solutions that look kind of like this. These are streamlines. This was presented by Hristov et al. 2003 in Nature that show a numerical solution to the Rayleigh equation. And so you can see we have these alternating cells of streamlines. We match the velocity of the waves at the boundary. And it actually creates these alternating patterns of high and low pressure across the wave crest. Low pressure is aligned with the upward wave motion. This wave is going from left to right. So this is the upward stroke of the wave orbital motion. High pressure aligned with the downward stroke of the wave orbital motion. And this creates an energy flux as well. I like to relate this to a bicycle pump that takes work to pump up your bicycle tire. You push down on the high pressure. It's hard, it takes effort. And then when the pump chamber is empty, drawing up on the low pressure also takes energy. It's hard to refill the air inside that piston. And so the wind is effectively doing this pump mechanism over the waves, transferring energy mechanically. Um, and then the gradient of pressure across this surface form creates a net force on the surface, which we call the form drag. All right, so this gives us lots of feedback between that wind profile, right? We have a wind profile U of Z that depends on the roughness length, but we put in that wind profile into something like the Rayleigh equation that gives us the growth rates for the wave modes at the surface. Those growth rates are important for the roughness, and then that roughness is what sets our boundary layer shape, right? So this go in this sort of feedback loop between the wind profile, the growth rate, the roughness, the wind profile. All right. So just a quick summary. I know I'm taking a long time with this introduction. I swear I'll get to the measurements soon. The marine boundary layer in the atmosphere has these flux profile relationships, which have been shown to be fairly well described by Monin-Obukhov similarity theory, i.e. these log profiles with stability modifications. Measurements have shown the profiles tend to look pretty similar to what we see over land with some modifications. If the roughness, that coefficient can be determined with wave parameters, or because there's a tight correlation between the waves and the wind, sometimes just mean wind speed also. But in reality, that drag is being determined by these complex small scale fluid flows of wind over waves that has several different parts. It has linear growth, there's shear instability, there's occasionally flow separation, and there's other effects that I didn't have time to talk about, papers by Belcher and Hunt about some of the turbulent interactions with the waves. There's ways to implement waves into, in a bulk sense, into these MO algorithms through a roughness parameterizations from Z0, and also spectral coupling, which can be informed by some of these wind over wave theories like Miles' theory, which gives us growth rates, which can be related to Z0 and roughness length. All right. And then these have strong feedbacks, right? So all of these, both the bulk solutions and the spectral solutions require some amount of iteration to go around in this circle and stabilize before we get to something a little more stable because of these strong coupled feedbacks. All right, so I have a couple questions that I'd like to address. I mentioned the TKE equation, the energy budget. I'm a big fan of looking at the TKE equation. One thing that isn't mentioned is how energy is conserved between wave growth and Monin-Obukhov similarity theory from the boundary layer. So we know that waves carry with them a large energy flux. That energy ultimately comes from the wind, but in our theories from most, we didn't have anything that could send energy down into the waves, right? We just have dissipation in the atmosphere. In our balance, we have buoyancy fluxes, but there's no way to send energy into the waves. But we know there's waves on the surface of the ocean that are carrying with them lots of energy flux. And so there's some sort of missing component in this with the energy budget. I mentioned that this pressure pumping mechanism, it's very hard to make direct measurements of pressure or pressure work, the pressure velocity correlations in the field with some of the specifics of putting pressure sensors in a flow. You tend to create a pressure pattern by putting something in the way of the flow. And that is usually called wind noise in pressure sensing communities. It's very hard to get rid of wind noise. It can be directionally dependent. And so it's fairly hard to verify some of this stuff in the field. And then Additionally, our original arguments for this log layer for having the 1 over z relationship for shear was that we had no scaling parameters that we could use. But when we add waves at the boundary, we actually have lots of scaling parameters we can use. We have wave heights, we have wavelengths, we have wave orbital motions, we have phase speeds, group velocities. There's all sorts of additional scaling parameters that we can throw into this. And so there's been folks who have called into question these original scaling arguments on that basis, right? We have a slightly different boundary matching condition. You would assume the no slip or velocity matching condition would mean that the surface wind velocity has to match the wave orbital motion. And so it's unclear and it's been questioned whether these scaling arguments still hold or not. All right, so I'd like to look into these things with some of our measurements. This is where the towers come in. This was on the left. This was shown in my title slide. Um, that was our deployment in spring of 2022. The right, this is our tower from the fall of 2022. I mentioned they were deployed in Buzzards Bay in Massachusetts. So this is the arm of Cape Cod right here. Boston is up this way. Woods Hole, for those of you who visited Woods Hole, is right here. This island down south at the bottom, this is Martha's Vineyard. Our tower was right here in Buzzards Bay. So this is a fetch limited basin. It's a little longer fetch to the southwest, but generally the fetch was 5 to 10 kilometers. So it limited us to fairly short wind waves, which is great. We didn't have to deal with the complicating influence of swell. It also let us put our sensors pretty close to the water. The tides are not all that big here. Um, and the wind-driven water level variations are also not super big. So it let us, estimate the size of the wind waves from fetch and put our sensors fairly close to the surface. Additionally, it's relatively deep for the fetch that we see in this basin. And so the waves are, even though they're short waves, they are sort of restricted to the deep water wave regime from the depth to wavelength ratio. Okay. So the hope is that these would be, representative of deep ocean waves, sort of like a natural laboratory. Um, you'll see at each of these booms, we have a sonic anemometer paired with these four discs. This is our intake for our pressure sensors. This is a design that has been tested in the lab to minimize what I mentioned before, wind noise, the effect that the putting something in a flow will affect the pressure that you measure at the pressure instrument. So these were paired at 3 of the booms, and then we also had a laser wave gauge. I've called it a LiDAR in the past, but wind LiDAR is becoming a lot more prevalent, so it can be a little confusing with wind LiDAR studies. So I'll call it a laser wave gauge for now. And all of these sensors were aligned, logged simultaneously from the same data logger, so the same clock, and we aligned them in space as close as possible so we could get estimates of velocity, pressure, and the water elevation underneath at the same place in the same time. And what that looks like, here's a snapshot of a time series during one of the higher wind events we saw in the spring of 2022. The top panel shows the pressure from our 3 different booms: blue, the lowest, boom 1, orange in the middle, and then yellow, the highest boom. And then the bottom panel shows the elevation from the laser wave gauge. This is a time series, but you can think of the waves as going from right to left and the wind from going from right to left in this image. So you can see that the pressure varies up and down with the waves underneath. And there's some interesting, more complicated patterns, which we'll talk about in a little bit. But this allows us to do measurements of coherence, both with the velocity and with the pressure, and start to understand how much of these atmospheric motions are being driven by the wave field underneath. All right, so here's a brief, really quick overview of the 2 projects in the spring. The top panel shows wind speeds. The left side shows spring, the right side shows fall. The middle panel shows the significant wave height. And the bottom panel shows the magnitude squared coherence between the pressure, the atmospheric pressure, and the sea surface elevation eta. All right, so this is the yellows indicate stronger wave influence, the blues lower wave influence. But you can see most of the time for both of these projects, there's a measurable influence of the wave field in atmospheric motions around those wave frequencies. It's fetch limited, so the waves were sort of zero point 0.3 hertz. So that was an average wave period that we tend to see. Wave heights, they were pretty small or fetch limited, but during the higher wind events, they would get up to about a meter. Um, and that was enough to really see some of this influence. Not the focus here, but this circle I have highlighted shows one of the higher wind speed events where we see decent magnitude squared coherence. We actually see these narrow, much higher bands of coherence. We tend to see this when the wind died really rapidly and the wave field persisted. Um, I am not going to focus too much on the swell-driven fluxes. I'm mostly focusing now on the opposite, on the wave growth relations, but I think that's an interesting topic. So we'll mostly focus on the effects of these higher winds when we also saw fairly high correlations. All right, so to jump right in, I've spent a long time on the background at this point. This is the turbulent kinetic energy budget. It's dimensional. It's not non-dimensionalized yet, like is proposed, is often shown in Monin-Obukov theory. The vertical here shows epsilon, the TKE dissipation rate. The horizontal shows the production plus the buoyancy. Because the production involves a gradient, this is estimated between their pairs of booms, between boom 1 and boom 2 for level I or level 1, between booms 2 and 3 for level 2. And for the most part, this shows that this is a pretty good TKE budget, right? This is in agreement with what we would expect in the log region, the boundary layer, and it holds for nearly all of our measurements for these 2 months. So first order, this looks pretty great with what we would expect from a typical log boundary layer, which is one of those underpinnings of MO theory. We'll note that at the highest energy levels, all the way at the top right here of this plot, we start to duck a little bit behind to the right of this dashed black 1-to-1 line. Okay, so we'll talk about that more in a little bit. But really, that's sort of a second order effect that happens in a small subset of these measurements. Okay. If we then go and look at the similarity functions for shear and dissipation rate, we see really good agreement with previous measurements. So here, the blue diamonds with the vertical lines, these are the estimates of non-dimensional shear from our towers. The gray circles with error bars, this is the data from Edson et al. 2013 from the core paper. And the blue line, this is the shear stability function used in core 3.5. And then the green line is a Businger-Dyer stability function that's used sometimes over land. All right, so you can see we have really good agreement with both the previous shear data presented from Edson and with this core stability function. So it seems like, on first glance, this seems to work fairly well. We expect on average that the shear is acting like it would over other patches of ocean. And similarly, it depends on the stability parameter Z over L. And it changes the shear, roughly factor of 4 for very stable conditions and maybe a factor of 0.5 for very unstable conditions. The dissipation rate, it doesn't look quite as close to these proposed functions as the shear does, but it's pretty close. We match the convection limit here. But we see we have slightly less dissipation than is predicted from some of these other functions. So the orange curve here, phi m minus zeta, this is what would solve the non-dimensional TKE budget that I showed in slide 3. And then orange, this is the Businger-Dyer over land function. Okay, so you see the dissipation doesn't match quite as well, but it's pretty close to this type of form. Okay, and so I'm going to make a little bit of a detour, so bear with me for this one. I mentioned this wave mechanism for pressure work. that I will describe really quickly before we return to MO similarity theory. As a reminder, in the bottom left here is that image from the numerical solution to the Rayleigh equation that gives us these alternating high and low pressure patterns that are correlated with the vertical motion in the air. So what I'm going to show you here in the center is co-spectrum of pressure work, PW correlations, which results in this energy transfer via this sort of bicycle pump mechanism. They're co-spectra, so they depend on frequency. And this is specifically the wave coherent part. So it's the part of the pressure work that we measure that is coherent with the oscillating free surface on the boundary as measured by the LiDAR. So this is actually a hidden term in our TKE budget that I've ignored so far, but it turns out that the vertical gradient of PW, of pressure work, is a term in that turbulence budget, and it's how we might connect this sort of wave growth mechanism with the energy in the TKE equation. And then if it's vertically integrated, then the pressure work at Z equals 0 would be the energy flux to the waves from this full boundary layer integrated effect of this wave source term. Okay, this is sort of a complicated plot. We'll get through it, I swear. So I'm going to show you the wave coherent pressure work co-spectrum. It's normalized so that these fit on the same plot. And I'm going to step through a couple different values that are binned by 10-meter wind speed here. Okay, so blues, light winds, reds, high winds. This is hard to put on log plots because it changes sign. So positive values means upwards flux. Negative values means downward flux, so wind to wave transfers. And then another thing to note, this layer where these circulations change sign, called the critical layer, this happens where the local wind speed, U of Z, is equal to the phase speed of the waves underneath. Okay, so we call that that reflects in a frequency spectrum because waves at different frequencies travel at different speeds. So for each wind speed bin, this will shift slowly to the left in frequency space or towards faster waves that happen at lower frequency. And we'll see how this normalized co-spectrum changes with wind speed and how that sign changes. Okay, so at the lowest winds, we have mostly waves that are faster than the wind, and that is sending a flux, an energy flux upwards into the atmosphere at these low blue wind speed bins. As we step through, we'll see at moderate wind speeds, 5, 6, 7, 8 meters per second, the critical layer frequency shifts to the left. And as it does, we start to see wind faster than waves on the right that are resulting in a downwards energy flux. And then the waves faster than the winds are still sending energy flux upwards. And as we move to the highest wind speeds, this critical frequency is to the left of where our wave spectrum is. And so all of the waves are traveling slower than the local wind and sending a downwards flux for these highest profiles. And it's not a coincidence that this downwards flux looks sort of like an upside down wave spectrum, right? These are specifically the motions that are coherent with the measured wave spectrum. And so they have sort of reflected that sort of classic wave spectrum-like shape in this shape here. All right, this is from the lowest boom height. We have 3 booms. They don't all look quite as clean as this one, but we can show a similar plot to this as it varies vertically across our array. The vertical shape is important because it's actually the vertical gradient of this term that appears in our energy equation. All right, so it is noisier at these other booms, but we do see a fairly similar trend. And in particular, notice at the highest winds, we see these downward fluxes that are apparent in all 3 booms. I've added one more panel on the right here. This is the magnitude of the pressure work. This is sort of what I'm normalizing each of these co-spectra by. And you'll see that it goes up several orders of magnitude from the low wind speed cases, and it decreases with height at these highest wind speeds. So the highest pressure work close to the surface, lowest up at 7.5 meters height. Okay, so this decay rate will result in a d by dz of pressure work, which will give us a sink in our energy equation in turbulence. All right, so this was a detour, but I'm going back to the MO stability functions. This is the function for dissipation. And now I've zoomed in close to zero because when we have really high winds, it tends to be close to neutral stability. And I have picked out in orange the points where we have really strong high values of this wave coherent pressure work from the rest of the data set. And what you see is that as we increase this wavy pressure work, we see even smaller dissipation rates than we would expect from either the baseline or from, these benchmarks that have been averaged over lots and lots of data here for overland and over ocean empirical functions. Okay. So that's consistent with this idea that the waves are drawing energy down out of the atmosphere. There is less energy sink through turbulence, and there's more energy sink through surface waves. Um, most of when we apply MO theory, though, we mostly care about the shear profile. That's usually what sets our wind speed into a stress at the interface. And when we look at the shear stability function, we don't see quite the same thing. There's maybe a little bit of a trend here, but these error bars are quite big, and for the most part, these are not statistically that different from this baseline blue curve that we have here. Okay, so maybe if you squint, these highest points are starting to be have error bars not overlapping with our sort of baseline small pressure work data, but shear is much, much less affected um, than the dissipation rate. So we can quantify the net effect of these energy transfers and try and make sure we really understand how this energy is impacting our budget by looking at the vertically integrated budget across the whole array. So I mentioned when you integrate vertically, you get this gradient of pressure work becomes just the pressure work at the interface. And we can relate that to the wind wave growth term that appears in our spectral wave models. Okay, so now I'm highlighting a high wind event that happened in the spring of 2022 over several days. This is what I was circled on my background wind speed plot that overviewed the wind speed and wave heights over the experiment. The blue dots and the running mean blue curve. This is the integrated turbulent kinetic energy budget with respect to the production, buoyancy, and dissipation rate terms across our three booms. We see that it's positive, which in this case means we have more production than we have dissipation, or there's a dissipation deficit. There's less dissipation than you would expect to close this energy budget. If we compare that with our pressure work, our wave coherent pressure work, we see that it matches quite nicely, which is the pressure works, these orange squares. We can also compare that to the frequency integrated source term to a wind wave model, which is shown in purple. I use the Peter Janssen's wind wave input in this case. There's some error bars on what some of the growth rate coefficients are, but we can see that also matches quite nicely for this storm. So this gives us really nice, tidy picture, I would think. The shear is relatively unaffected. There is an energy sink into the waves, so that mostly comes out of the dissipation rate and not any shear production. And so in some ways, yes, we're violating MO theory in that the dissipation source function or the dissipation MO function doesn't really look like it would in other situations. It's depending a lot on wave parameters. But the good news is the shear is unaffected, and so that's really what's impacting our bulk fluxes when we put them in, put a wind speed in to get a stress estimate. And that seems pretty unaffected even in these high wind cases where we see this wave influence. So this is a good, sometimes they say not to try it again if you've already got it. And so the fall data set doesn't look quite as clean, unfortunately. This is a hurricane remnants that came over our array in the fall of 2022. Again, the blue is the dissipation deficit. The orange is the wave coherent pressure work. The purple is the spectral wave model input source term. We see worse agreement overall. They're a little closer between the pressure work and the wave model, but we have a much bigger dissipation deficit than we can explain with some of these wavy terms. All right, so uh, unfortunately, this didn't quite pan out quite as nicely as the spring data set, but it shows, a similar qualitative trend. The magnitudes don't match perfectly. One thing I haven't discussed or shown quite yet, there's a few additional terms that are typically assumed to cancel each other in the TKE budget. This is the turbulent, the wave incoherent pressure work, and what's called the TKE flux, or sometimes the triple velocity correlation. These are turbulent, not wave coherent terms. They're assumed to cancel each other in most boundary layers. Um, I can compute them, but I haven't been including them because they don't always cancel in this data set, and it's depending on a couple different things. So here I'm showing these residual terms as they would appear in the vertically integrated budget. So this is not vertically integrated. I'm showing the gradients in the plot. This is vertically integrated, which would just be the difference across the array. We see they're really correlated on average over several orders of magnitude. The orange is if you would use the full range of frequencies, and we have a turbulent pressure that's about 4 times higher than the turbulent TKE flux. Um, and I'm pretty sure this is because there's some issues with the low frequency pressure in distinguishing sort of the like mesoscale meandering atmospheric pressure from the turbulent components, which has kind of been a challenge. If you restrict the integration of these terms to timescales lower than 0.001 hertz, we actually get fairly close one-to-one agreement, except at these highest winds when something else is going on, when we really see some of these wave um, mechanisms turning on. So uh, there's still a little bit to be done with the residuals. It's much harder to measure these terms. They're typically assumed to cancel. Seems like they do across specific frequency bounds, but I haven't been fully able to pick apart some of the really low frequency meandering that seems to cause some of this deviation here. Okay, so I'm at about 45 minutes, I think. I want to leave room for questions. So as a summary, just really to highlight the first figure I showed here, most of the time this TKE budget works, right? This is the first order effect, production equals buoyancy plus, or production plus buoyancy equals dissipation rate. This works most of the time and is generally the first order effect. And that's why, leads to these shear functions working most of the time. These high wind events, we can really observe this wavy pressure work mechanism, this pumping mechanism by the waves that generates a dissipation deficit, right? It takes energy out of our boundary layer that would otherwise go to dissipation. And in some cases, we can balance this energy budget at that second order here, right? The first order balance, production, dissipation. The second order, we have this sort of 10% or so residual that seems to balance with dissipation deficit and pressure work. Doesn't always work because of some of these other turbulent terms, which are also hard to measure. But the takeaway is that, in these conditions, the shear is relatively unaffected, and we think that the bulk flux algorithm should work well, even though we're close to the surface and can measure wave influences on this boundary layer. All right, so I'll stop it there and have some time for questions, but thanks for bearing with me through the long background introduction. I hope folks found this useful and valuable.
Thank you so much. Great talk. Uh, Questions for Seth? So Roger Samuelson has his hand up.
Hi, Seth. I guess I'll go ahead and ask, though I could walk upstairs later today and ask the same question. Uh, you talked a lot about the energy balance in these high wind events. Have you thought at all about the momentum balance and where that flux is going?
Uh, Yeah, the momentum balance is pretty much d tau dz equals zero. Um, we have, a vertical array of tau. There's a small decay vertically away from the surface. That's pretty consistent with a linear decay over a full boundary layer height of hundreds of meters. Um, and yeah, uh,
Sorry,
the
just to clarify, what I meant more, is it going into the waves? Can you tell in
oh,
these
you mean
places where, yeah, so is the momentum going from the wind to the ocean gets split between the waves and some sort of mean other non-wave thing?
right? Okay, so I mentioned the this pressure work mechanism as the pumping on the interface. But the corollary to that is the pressure slope correlation or the form drag of the pressure pattern across the waves. Is that what you're discussing?
Yeah, that's right. So I guess, yeah, I'm interested to hear. I think I know the answer, but I'm not sure. So,
Yeah, I mean, so in theory, the vertical velocity has a pretty tight relationship with essentially the slope at the interface through, linear wave theory. And so you can relate the uh, wave supported momentum and the wave supported energy with the phase speed. So the energy flux is the phase speed times tau, and the form drag would be the pressure slope instead of the pressure velocity correlation. The one of the issues that you run into a little bit is even being this close to the surface, uh, you would have to extrapolate a little bit down to the interface. And in terms of momentum, because of this phase speed relation, the momentum's really shifted towards higher frequencies and the energy is shifted a little bit towards lower frequencies, just because of this phase speed relation. So we can see part of this pressure slope, but the meat of the pressure slope is at even higher frequencies that are just hard to observe at the heights that we're sampling at, even if it's tens of centimeters above the wave crests. Um, so I have found it a little easier to measure the pressure velocity than the pressure slope correlations because of this. You can do it at slightly lower frequencies and a little higher up from the surface. A lot of it is of interest though, a lot of the theory is developed in terms of the wave momentum flux with respect to the total boundary layer flux. Um, it's just a challenging thing to measure directly.
okay, thank you.
I will say if you can do a similar type of wave coherence on the co-spectra, you do tend to see similar, wave spectrum shaped bites out of the UW co-spectra. It goes in both directions and it seems fairly well matched with the pressure work if you apply a linear theory to convert between them. Um, I haven't shown that, but it's something I've seen in a few of these data sets.
Great. I see that Megan has her hand up. Megan, go ahead.
Yeah. Hi. Really interesting. By the way, I did put a link to your paper into the chat, so everyone should go and download that. So very interesting about your looking at the wind relative to the wave speed. And I'm just wondering, do you have advice on these bulk algorithms depend upon wind speed relative to the surface currents? And oftentimes we don't really know very much about the surface currents. And so we just use daily averages or 10-meter currents. In terms of really what the physics represent, what should that surface current be?
Yeah, it's a good question. Um, I also mostly ignored surface currents here. We do have tides, but they go back and forth, and so on average, they sort of tend to um, go away if it's a symmetric effect. Currents, it's a really, we don't, the, this boundary layer theory doesn't quite apply to the ocean surface and the near surface layer in quite the same way as it seems robust in the atmosphere. So it's harder to take those 10-meter currents and project them up to an interface condition. These wind wave theories all tend to be neutral, stability, zero surface current in a reference frame following a wave phase speed is usually how they're posed. And so they don't often deal with surface currents either, or the assumption is you can put yourself in a reference frame where that is, negligible. So it's mostly been ignored, but it's an interesting question. I think in particular, these growth rates for surface waves, they have there's a lot of variability in all the existing measurements, like 50% or so, plus or minus, sometimes more. And a lot of it, it's sensitive to the shape of U of Z, and that can be easily modified by a lot of things. Some things more easily than wind speed. Stability is the one that we often deal with, but there's can be small. I would assume if there was a surface current that a flow was interacting with, that might, shift it relative to the wave speed or something in a way that could impact the profile and the shape of the profile, which then feeds back on the growth rate and the drag. And so I wish I had like a general rule of thumb for you or something that I could just tell you this was the answer. And I think it's a difficult question. And um, yeah, I think surface currents are really interesting and probably a ripe topic for more research.
Great, thank you.
Any other quick questions? I'm sure people have more, but we are just about at the end of the hour. And so maybe we will give Seth another round of applause and thank you for a really engaging and interesting talk.
Well, thanks everybody for listening, and thanks for letting me give the first and then the 100th Oasis seminar.
Thank you so much.